The question that I have is, could you describe the triaxial test? I will not get into the finer details. We'll keep the discussion at a conceptual level. If you compare the triaxial setups made by two different companies, they might look a little different from each other, but at a conceptual level, they should be pretty similar. In this testing method, we use cylindrical soil specimens. These are two of the most commonly used sizes. The soil specimen is placed between two loading platens like this. Then we wrap the specimen with what is called a triaxial membrane and put a couple of O-rings like this so that the water cannot flow from outside to inside or inside to outside. The whole thing is then placed inside what is called a triaxial cell, which has all kinds of bells and whistles. I have shown those features that are conceptually important. Number one, there are drainage lines like this. If I keep valve A open, then the water can flow from inside of the specimen to outside or outside to inside of the specimen. There's usually a drainage line at the top and one at the bottom. So water can flow either in the vertically upward direction or vertically downward direction from the specimen. Suppose, say, during loading, the specimen is trying to shrink, right? So what that means is it's going to try to push water out of there, right? So water will come out through these drainage lines, and as long as you keep this valve A open, it'll come into this U-tube. So by keeping track of this water level right here, we can figure out how much water came out of the soil specimen, which should be exactly equal to the change in volume of the soil specimen, right? In some tests, we don't want to let the water come out or come in, so what we do is we keep this valve closed. Such tests are called undrained tests. So obviously volume of the specimen cannot change in that case because water cannot come out or go in, and therefore the total volume cannot change. But when you do something like that, the pore water pressure inside the sample could change. So usually what we do is we attach a pore water pressure transducer somewhere here so that it can keep track of the pore pressure inside the soil specimen. Also, I might want to mention that these days, instead of using a U-tube, they might use a volume change transducer, which is again a pressure transducer or highly sensitive pressure transducer that can pick up even a small change in the elevation in the U-tube kind of thing, right? So to sum up the drainage facilities here, in a triaxial cell, you can either allow drainage or prevent drainage. And when you allow drainage, the volume of the specimen could change. It could either decrease or increase, and we have a way to measure that. When you don't allow drainage, the volume of the specimen cannot change, but the pore pressure could change. Again, we have a pore water pressure transducer that can keep track of the change in the pore water pressure. All right, so let's talk about some of the other features here. So we put the sample inside and assemble everything, right? What else do we have? We have a cylindrical cell. There's obviously a base here that contains all these drainage lines, and the cell has a top. When you put the top and clamp everything down, you can fill the cell with water. So usually that's what we do. We fill it up to something like this, up to a level like this, so that the specimen is completely immersed in water. The top also has a little opening here that the vertical loading rod could slide through. So this part is pretty sophisticated. It allows the loading rod to slide through without exerting any friction, but on the other hand, it prevents leakage of pressure applied inside the cell. All right, so after you fill the cell with water, then you can apply what we call cell pressure. So when you apply the cell pressure, the water is now subjected to that pressure, and that applies an all-around pressure to the specimen. here I have shown the stresses acting on the specimen. Sigma C is the cell pressure, so that's an all-around pressure. It acts around the specimen. Then when we want to shear the specimen, we increase the vertical load, which would increase the vertical stress. So the increase in vertical stress is what is called the deviatoric stress, delta sigma. So the total vertical stress will be the cell pressure plus this deviator stress. This is a cylindrical specimen with a surrounded by water, right? And therefore, the two principal stresses are equal to each other. All right, sigma 2 and sigma 3 are equal to each other. Sigma 3 is exactly equal to sigma C. But there could be a pour water pressure inside the specimen, right? Remember, if I keep this valve closed, pour pressure will build up, right? So U may not be 0. So what that means is, while these guys, sigma 1 and sigma 3, serve as total stresses, they are not the effective stresses. To find the effective stresses felt by the specimen, I need to subtract the pour water pressure from these total stresses. So here I wrote a little bit about the differences between the drain test and the undrained test. So what exactly do we do? The whole discussion here centers around testing a saturated specimen, all right? Typically, specimens are not fully saturated. This is particularly true for specimens brought from the field. So the first thing you want to do is to make sure that the specimens are fully saturated. If they are not, your pour water pressure measurements or the volume change measurements will not be accurate. So one of the techniques that we do, especially in clay soil, is to apply an initial pour water pressure called back pressure. So what this does is, if there are air bubbles inside the specimen, this back pressure will squeeze those in and increase the degree of saturation. But when you apply this, you don't want the specimen to blow up from inside out. So what we do is we also increase the cell pressure simultaneously so that the net change in the effective stress is 0. So how much back pressure do we apply? Well, that is something that you have to figure out by a trial and error procedure. But usually maybe like 10 psi, 15 psi, something like that. In clay soil, nothing happens instantaneously. So after you apply the back pressure, you have to let it sit there for a while. If it's a granular material like sandy material, then you have other ways to increase the degree of saturation too. Supposing, say, you are making a sandy specimen right there in the lab, right? So usual procedure is to make the specimen dry, completely dry, and then the first thing you do is to flood the inside of the specimen with CO2, carbon dioxide. And then you send the water through in order to saturate. So carbon dioxide dissolves in water, and therefore eventually you get a much better saturation that way. You can still apply a back pressure just to make sure that the degree of saturation is high enough for all the measurements to be accurate. There are two phases to the loading that we apply to a triaxial specimen. The first phase is called the consolidation phase. So basically what we do here, we increase the cell pressure to a predetermined value. Well, what do we do with the valve during this part? Well, we keep the valve open for the test types called CD and CU test, and we keep the valve closed for the test type called UU test. I'm going to talk about these in the next section. If you keep the valve open, consolidation is going to take place, right? Because you just applied a total stress both in the vertical direction and the horizontal direction, and the consolidation process will be initiated, and it's going to take some time, and the time obviously depends on the soil type, permeability, compressibility, and what have you. So everything that we have learned earlier in the section on consolidation applies here. So what you do is you monitor the water level in the U-tube. You know, the water is going to come out, right? So the water level is going to go up. So you monitor that and wait until it tapers off. That's an indication that the primary consolidation, due to that increase in the cell water pressure, has come to an end. The second phase is called the shearing phase. So basically, you are going to increase the deviator stress, delta sigma, until failure, but you do that gradually. As soon as you increase delta sigma, sigma 1 becomes different from sigma 3, and then the shear stress inside the specimen becomes non-zero, and then of course it's going to increase gradually as you increase delta sigma. At some point the specimen is going to fail. Now why does the shear stress increase? If you can visualize the Mohs circle in your mind, if the two principal stresses are equal to each other, Mohs circle is basically a point, right? And therefore there is no shear stress in the specimen. But as soon as the two principal stresses become different from each other, then the Mohs circle has a size. There are some planes that have shear stresses, right? Supposing say the deviator stress at failure is delta sigma f, then sigma 1f, which is the vertical stress at failure, is sigma c plus delta sigma f, and sigma 3f, which is the horizontal stress at failure, is exactly equal to sigma c, because we don't normally change sigma c. We apply a cell pressure and keep it constant during the test. And in addition to that, of course, if there is pore water pressure, we also will keep track of the value at failure. So these are the three quantities we will need in order to evaluate the shear strength parameters of the soil. So here are the three test types that I briefly mentioned in the earlier slide. Consolidated undrained test, abbreviated as CU test, consolidated drain test, abbreviated as CD test, unconsolidated undrained test, abbreviated as UU test. Remember we talked about the triaxial test consisting of two different phases, right? Consolidation phase and the shearing phase. For a CU test, consolidation, the first part is done under a drain condition. In other words, you allow drainage, you leave the valve open. The shearing part, the second part, is done with the valve closed. In other words, you do that under undrained condition. Now you know the meaning of these two letters, C for consolidation and U for undrained. And similarly, in a consolidated drain test, the consolidation phase is done under drain condition and the shearing phase is also done under drain condition. So this is truly a drain test all the way through. In a unconsolidated undrained test, the consolidation phase and the shearing phase both are done under undrained condition. So you will keep the valve closed throughout. And when you allow drainage, we know the volume is going to change, but the pore water pressure will eventually dissipate. If it's a clay material, it's not going to happen right away. So you have to wait until that happens, but eventually the pore pressure is going to be zero, right? And when it's done under undrained condition, the volume cannot change, but the pore pressure could change, and so on. Let's talk about the total and effective stresses. Supposing, say, these are the principal stresses at failure, and the pore water pressure at failure is U sub F. Like I said earlier, the stresses applied on the outside of the sample are the total stresses. So here, sigma 1F and sigma 3F are the total stresses. And if you were to construct the Mohs circle utilizing the total stresses and evaluate the shear strength parameters C and Phi, they are called the total strength parameters. Now let's define effective stresses like this by subtracting the pore water pressure from each of the two principal stresses at failure. And if I were to now construct the Mohs circle utilizing these effective stresses and evaluate my shear strength parameters C prime and Phi prime, they are called the effective strength parameters. Each set has its use in practical calculations, and we'll talk about them later. I think I gave you sufficient background about the triaxial testing method, the three types of tests that we normally do, the stresses, the type of stresses we get from the three types of tests, and the shear strength parameters we get from them. Now you can read more details about these from our textbook or any other similar soil mechanics book.